Okay, so let's really unpack this. Imagine a machine, right, with like absolutely no prior knowledge, no equations programmed in, no Newton, no Einstein, just nothing. And yet it sat there, it observed reality, and it didn't just copy or refine existing ideas. It created entirely new laws of physics, completely from scratch. I mean, this isn't science fiction anymore, is it? It feels like a profound shift in how we even think about discovery itself. So today we're doing a deep dive. We're looking at an article by Srinidhi Ranganathan, and the title is pretty provocative. When AI with zero knowledge discovered new laws of physics and outsmarted Einstein. Our mission really is to explore this, well, it's an astonishing breakthrough. We want to understand the methods, these radical methods behind it, and really try to grasp what these new laws might mean for how we see the universe. This is where things get properly interesting, where your perception of reality might just get a serious update. This is the mind-blown part.
It really is. And the concept itself, this zero-knowledge physics discovery, it's not just about having a clever AI, right? It genuinely challenges everything we thought we knew about how science progresses. For centuries, I mean, our understanding of the cosmos has been built bit by bit, based on human observation or intuition, the accumulated knowledge of generations past. But this AI, it had none of that baggage, no human preconceptions. And somehow it unveiled aspects of reality that are, well, demonstrably true. And often they seem simpler or maybe more precise than the theories we've relied on for hundreds of years. It's a moment that really forces us to question things, not just the universe, but our own methods, how we inquire, what it even means to know something. It's profound.
Okay, let's start at the beginning then.
Yeah.
How on earth did this machine, starting from literally zero knowledge, pull this off? The article mentions this secretive quantum research lab,
Ugh.
codenamed Project Episteme Zero.
Mm.
What was the setup? What made this experiment so audacious?
Well, the audacity, I think, was precisely in its deliberate minimalism. It's such a stark contrast to how human scientists usually work. The researchers, they built this neural AI architecture, right? But it was designed specifically to function without any pre-programmed human inputs. So think about that. It wasn't fed existing scientific models, no theories of gravity, no electromagnetism, nothing we take for granted. And crucially, it wasn't even given numbers or mathematical symbols as foundational concepts. It started from an absolute blank slate, devoid of any language, any math framework that we humans use to describe the world.
Wow.
Yeah, imagine trying to understand the universe without even knowing what the number 1 is or what an equal sign means. That was literally the AI starting point.
That is just mind-boggling. Okay, so if it had no knowledge, no numbers, no equations, what did it actually eat? What was its diet? What raw information did it get to even begin understanding the rules of the universe? The article stresses this. No labels, no formulas, just pure movement, pure observation.
Exactly. Its diet, as you put it, was purely raw, unfiltered video data, just streams of natural events. Think of it like pure sensory experience, almost like a newborn seeing the world for the first time, maybe.
Mhm.
But, with this unparalleled capacity for processing that raw input, it watched countless hours of, well, seemingly simple phenomena.
Mhm.
Pendulums swinging back and forth,
Mhm.
planets orbiting the sun, particles colliding in accelerators, ripples forming on water, even complex stuff like the flow of fluids. And crucially, no human labels attached, nothing saying this is gravity or look, conservation of energy.
Right.
Its only instruction was remarkably simple, but also incredibly open-ended. Just find the rules.
Mhm.
It was this unprecedented empirical approach, letting the AI build its understanding from the ground up, purely from observed patterns, relationships it found in this huge, unstructured data set.
And this is where it really parts ways with the human scientific method, isn't it?
Right.
Because we build on this colossal structure of inherited knowledge. Newton, Einstein, Maxwell, all the giants. This AI had none of that foundation. It started completely fresh. So how did that zero knowledge approach actually let it not just rediscover things we knew, but then go on to refine them and even create totally new laws?
Yeah, this is absolutely key to understanding the breakthrough. The AI wasn't taught physics like we teach students. Not at all. It was given raw sensory input, right? And tasked with finding patterns, but without the baggage of our preconceived notions or human cognitive biases. Our scientific progress, it's amazing, obviously, but it's often constrained by the theories and assumptions we inherit. We stand on the shoulders of giants, but sometimes those shoulders block the view.
That's a good way to put it.
Classical mechanics paved the way for quantum mechanics, sure, but it also threw up conceptual hurdles that took generations to get past. This AI, though, it started completely unconstrained. Its process involved something really advanced, a form of symbolic regression. So it would observe stuff, then it would compress this complex, high-dimensional data.
Like the video feeds.
Exactly, into abstract, low-dimensional variables. And these variables, they often didn't map directly onto our familiar concepts like mass or velocity. They represented deeper, perhaps underlying, unseen relationships in the data. Then, the really impressive part, it would test billions of hypothesis structures per second.
Billions.
Billions. Searching for mathematical expressions or symbolic ones that precisely describe the patterns it was seeing in those abstract variables. It's that computational scale, combined with its lack of human bias, that let it not just rediscover known laws, but then refine them, make them more elegant, more general, often more precise. It could explore parts of the solution space that human intuition might just never stumble upon, leading to genuinely new discoveries.
Okay, so it finds these things, and the article mentions the human reaction. From the physicists at Project Epistema Zero, it describes them as being both terrified and fascinated. That's a really strong reaction, almost visceral. Why? Why such an extreme response? What is it about a machine finding something so profound that it makes you feel fear and wonder at the same time?
Well, it really strikes at the heart of, I think, human endeavor, especially scientific identity. For centuries, we humans have seen ourselves as the sole architects of these grand theories describing the universe, right? We viewed this intellectual quest figuring out planetary motion, understanding the atom as uniquely human, a testament to our ingenuity, our abstract thought, our creative spark.
Sure, it's central to how we see ourselves.
Exactly. So to suddenly have a machine starting from absolutely nothing, no knowledge, not only replicate our greatest achievements, but then surpass our understanding, to find patterns and rules we missed, or maybe oversimplify, that's profoundly unsettling. The fascination, of course, comes from seeing this new, incredibly powerful way of discovering things. It promises to unlock secrets we couldn't even imagine before.
Right, the potential is huge.
But the terror, or maybe it's a deep sense of humility, it comes from realizing that perhaps our human-centric view of science, maybe even our own cognitive limits, have kind of confined us, that maybe we were only scratching the surface. It raises these huge questions about intelligence, creativity, the limits of human understanding. It's a moment that forces us to sort of redefine our place in the whole landscape of knowledge.
Okay, wow. Let's brace ourselves then. Prepare for that perspective shift. Because the AI didn't just, tweak existing theories. It apparently unveiled entirely new principles. Principles consistently backed by observation, often way beyond our human ability to measure that precisely. These are the laws that really, really make you rethink everything, the truly mind-blowing ones.
Yep.
So first up, the law of temporal harmonics. The AI stated, events synchronize in time not just by energy transfer, but by entropy resonance. Okay, what does that mean? It says when two objects interact, they don't just exchange forces, they also adjust to match their information vibration levels. Can you unpack that? Information and vibration levels, what is that? And why is this law such a big deal?
Right. This one is genuinely groundbreaking because it shifts how we think about interactions at the most fundamental level. It suggests there's this deeper hidden synchronization happening in the universe. When the AI talks about information vibration levels, it's not talking about like physical shaking or anything.
Yep.
Instead, imagine every object, every event has a unique kind of informational fingerprint or an informational state. It's a measure of its inherent complexity, maybe how its information is organized, or its unique pattern unfolding across time. So the law of temporal harmonics suggests that when systems interact, it's not just about exchanging energy and momentum like we normally think of forces. They also tend to sort of align or resonate based on these informational states across time. Think of it less like billiard balls colliding and maybe more like a kind of dance, where elements are seeking this subtle time-based informational balance, almost like tuning forks resonating. But instead of sound, they're resonating with information itself.
That's a really interesting analogy, a dance.
Yeah.
Resonating with information. And the article suggests this could be a revolutionary explanation for quantum entanglement, replacing Einstein's spooky action at a distance with something based on these time-based resonance fields. I mean, that would be absolutely monumental for quantum physics, wouldn't it?
Oh, absolutely monumental. Yeah. Quantum entanglement. It's been one of the biggest headaches in physics, right? Where two particles get linked instantaneously, no matter how far apart they are.
Yeah, the spooky part.
Exactly. Einstein famously called it spooky action at a distance because it just seemed to violate the speed of light, our cosmic speed limit. This AI law offers a completely different perspective, a profound alternative. Instead of some instantaneous, unmediated connection across space, The AI suggests a mechanism rooted in time in these resonance fields.
Mm.
So, if interactions are governed by these information vibration levels, it suggests that entangled particles aren't communicating across space in the way we usually think.
Okay, so how are they linked then?
Instead, they might be synchronized through a deeper fabric of reality, one where time itself plays a more dynamic, active role in linking and harmonizing events. Fundamentally, it implies the spookiness isn't about breaking the speed of light across space, but maybe it's about a pre-existing, time-based resonance connecting them, perhaps hinting at some nonlinear aspect of time or an interconnectedness we haven't grasped that allows this synchronization. It could genuinely reshape the whole conceptual framework of quantum mechanics. It's huge.
Wow, okay. Let's pivot slightly, but maybe to something just as big, impacting the whole cosmos. The fourth gradient law. This one apparently introduces a new dimension of influence. Quote, motion is influenced by three known spatial dimensions and one emergent, invisible vector shaped by energy flow curvature. Okay, simplifying that. It sounds like a hidden slope in the universe, something that subtly bends the paths of objects, especially things with extreme energy. A new hidden slope. How does that possibly fit in or challenge our current picture of the cosmos, especially when we think about gravity?
Well, this law has potentially immense implications, particularly for gravity and the large-scale structure of the universe. For decades, one of the biggest puzzles in cosmology has been galaxy rotation.
Right, they spin too fast for the gravity of the stars and gas we can see.
Exactly. They spin so fast that the visible matter, stars, gas, dust, just isn't enough gravitationally to hold them together. They should fly apart. So to explain this discrepancy, astronomers hypothesized dark matter, this invisible, undetectable substance that provides the extra gravity.
Makes up most of the universe's mass, supposedly.
Supposedly. But we've never directly detected it despite decades of searching. Now, this fourth gradient law, by proposing this hidden slope or this emergent vector, it offers a potentially revolutionary alternative. Imagine space itself isn't perfectly flat, like a smooth tabletop. Imagine it has these subtle, invisible, maybe currents or inclinations created by the flow and curvature of energy itself.
Like ripples on a pond, but in space-time.
Sort of. More like a very slight, almost imperceptible gradient on a cosmic billiard table that subtly influences the path of the balls, especially the fast-moving ones. If motion is influenced not just by our familiar three spatial dimensions, but also by the subtle, energetic curvature, it could naturally explain why galaxies rotate the way they do, without needing to invent an entirely new, unseen form of matter.
Whoa. So this hidden slope could potentially refine general relativity. The article calls it gradient relative mechanics, or GRM, and crucially, it might predict galaxy spin better than dark matter models currently do. Are we actually talking about a paradigm shift here? One that could just eliminate the need for dark matter entirely?
Yes. That is precisely the radical possibility this law puts on the table. And it's a monumental one. If this gradient relative mechanics, this GRM, can consistently and accurately predict observed phenomena like those galaxy rotation curves, maybe even the large-scale clustering of galaxies without needing dark matter, it would fundamentally rewrite our understanding of what the universe is made of and how it evolved. Dark matter has been this crucial yet totally elusive pillar of modern cosmology for decades.
Yeah, it's baked into everything.
Exactly. So if this hidden slope, this vector generated dynamically from energy flow curvature, provides a more elegant, more empirically solid explanation, it would simplify our cosmological models tremendously. Research would pivot entirely, right? Focusing on the intrinsic properties of space-time and energy flow instead of chasing hypothetical particles. It would genuinely be one of the biggest paradigm shifts in physics in over a century, right up there with general relativity itself.
Okay. Mind blown. Again, let's try another one that really messes with your head. The principle of causal echo. The AI proposed, every cause creates a fate reverse echo in spacetime, altering its own past probability state. Okay, simpler terms, effects subtly but measurably influence their own causes. This sounds like literal time travel stuff. How does that even begin to work, and what does it do to our nice linear idea of time?
Right. It definitely sounds like science fiction at first, this idea of retrocausality, the future influencing the past. It's mostly been stuck in philosophy or very theoretical quantum stuff. Our everyday experience is strict. Cause always comes before effect. Bang, then sound.
Always.
But this AI law suggests something more subtle, a measurable feedback loop. Now, it's really crucial to clarify here. It's not talking about, going back in time and preventing your own birth, the grandfather paradox stuff.
Okay, good. That gets messy.
Very messy. Instead, it implies that an effect, once it actually happens, might send this faint informational ripple backward through time. And that ripple slightly nudges or influences the probability of its own cause occurring in the first place.
Ah, probability,
Yeah.
not certainty.
Exactly. Think of it like a subtle whisper from the future, just gently biasing the odds of an event happening in the past. It doesn't rewrite the past event, but it might make it infinitesimally more or less likely to have occurred exactly as it did. It's a complete redefinition of what causality might mean, not just a one-way street.
So it's not deterministic time travel, but more like the future, giving the past a tiny probabilistic nudge. Okay. What's the deeper impact of that for physics, for our understanding of time itself?
The impact is potentially immense. This law suggests a way to actually test for time-symmetric physics in a new way. Many of our fundamental physics equations, they work just as well forwards in time as backwards. They're time-symmetric on paper.
Right, like playing a recording forwards or backwards.
Exactly. But our observed universe clearly has a direction, an arrow of time. Things break, they don't unbreak, entropy increases.
We remember the past, not the future.
Right. This AI law offers a potential mechanism to reconcile the time symmetry of the equations with the time asymmetry we experience. It suggests a much more interconnected space-time fabric, where events aren't just passive consequences of what came before, but they're also subtle, active participants in shaping their own history probabilistically. Causality becomes this dynamic, subtly interactive process across time. It forces us to rethink the very nature of cause and effect and suggests a much richer, more complex relationship between past, present, and future than our simple, linear intuition allows. It's a truly profound shift.
Okay, moving on. Let's talk about the rule of dynamic equilibrium. The AI states, systems do not settle at rest but oscillate infinitesimally around a quantum information center. This implies nothing is ever truly still. Even what looks like complete rest involves these tiny micro-oscillations, constantly balancing some kind of universal informational ledger. That sounds like it redefines stability itself.
It absolutely does. It's a profound redefinition of equilibrium. It directly challenges our classical intuition, that if you leave something alone, it eventually just stops moving, reaches a state of perfect rest.
Yeah, like a pendulum eventually stopping.
Right. This law suggests that true, absolute stillness is actually an illusion at the most fundamental level. Instead, even when something appears to be at rest, the system is in this constant, incredibly tiny, infinitesimal dance, oscillating. And it's oscillating around what the AI calls a quantum information center. It's constantly exchanging and rebalancing information. Now, this isn't just about, say, the thermal jiggling of atoms that we already know about or quantum uncertainty.
Okay, so it's something deeper.
It seems to be. It's suggesting a continuous, active, dynamic process that maintains equilibrium through these constant micro-oscillations. Like it's perpetually balancing the universe's books, its informational ledger. So every stable state we see is actually a point of dynamic balance between opposing informational flows. It's like perpetual motion, but for information.
Wow, okay, so if nothing is ever truly still, always in this informational dance, what's the real-world impact or the potential? How could that change how we understand things or maybe even manipulate physical systems?
Well, the impact could be really transformative, especially in tackling one of the biggest, most stubborn challenges in theoretical physics, unifying thermodynamics and quantum field theory.
Ah, the theory of everything quest.
Part of it, yeah. Thermodynamics deals with big stuff, energy, heat, entropy. Quantum field theory deals with the tiny stuff, particles, forces. And historically, these two huge pillars of modern physics have been really difficult to mesh together into one single coherent picture.
They seem to operate by different rules sometimes.
Exactly. But by suggesting that equilibrium itself is inherently dynamic and, crucially, information-driven, this rule of dynamic equilibrium offers a potentially surprising new way to bridge that gap. It implies that the rules governing energy flow and entropy on the large scale are intrinsically linked to this quantum dance of information happening at the tiniest scales. It could lead towards a deeper, more unified theory where information is seen as maybe the fundamental currency, driving both the micro and macro states of the universe. It basically redefines what stable even means, suggesting the universe is always subtly in motion, always balancing its information books.
Okay, one more major law to unpack here. The law of micro-macro entanglement. This sounds complex, the AI proposed. Every macroscopic event reflects a statistical mirror of entangled microstates governed by non-local wavefront memory. Whoa, okay, breaking that down. Big events mirror tiny quantum states. in some kind of holographic feedback loop. This sounds like it connects everything to everything else in a really deep way.
It really does. And this law directly attacks that traditional separation of scales we've always used in physics,
Hmm.
that deep divide that has compartmentalized how we understand the universe. Historically, it's been quantum mechanics for the very small particles, atoms, their weird interactions,
Uh-huh.
and classical physics for the big stuff, planets, galaxies, baseballs, us.
Right. Two different toolkits.
Pretty much. This AI discovered law suggests there's actually a deep inherent connection linking these scales. It implies that macroscopic events, the big things we see, aren't just emergent properties bubbling up from below. They might actually be statistical reflections of deeply entangled microstates. And that phrase in there, non-local wavefront memory, that strongly hints at something like the holographic principle.
The idea that all the information in a volume of space is encoded on its surface.
Something like that, yeah. Think of it like this. Maybe the universe, at its core, has this imprinted memory of quantum patterns, where information about the whole system might be encoded in its tiniest parts or vice versa, where large-scale reality emerges from and reflects back onto this deeper interconnected quantum fabric. It suggests that a tiny change in just one quantum state could, in a statistical sense, ripple or echo across macroscopic scales, even without any direct local contact, like a subtle quantum butterfly effect.
Okay, so if big events are statistically mirroring tiny quantum states, what does that mean for understanding complex systems? Could this explain things that seem random, like weather patterns or maybe even biological processes in a totally new way?
Precisely. That's one of the most exciting potential applications. This law could provide that crucial missing link between chaos theory and quantum mechanics. Chaos theory, deals with complex dynamic systems that are super sensitive to initial conditions, like trying to predict the weather accurately long term.
The butterfly flapping its wings.
Exactly. This law suggests that those seemingly random or chaotic large-scale events, weather, yes, but maybe also stock market fluctuations, the incredibly complex folding of proteins in biology, maybe even the emergent patterns of human thought. They might not be purely random or purely classical. Instead, they could still be reflecting an underlying, deeply entangled quantum reality, with information flowing and echoing back and forth between the micro and macro scales.
So quantum effects might be subtly shaping our everyday world much more than we thought.
That's the implication. It could unlock entirely new ways to understand complexity, predict behavior in these intricate systems, maybe even eventually control them by understanding and potentially manipulating these hidden quantum informational links. It really offers this unified perspective on the universe, doesn't it? From the smallest quantum jitters to the largest cosmic structures, challenging us to see it not as separate layers, but as one seamless, interconnected, almost holographic whole.
Absolutely mind-altering stuff. Okay, these discoveries are staggering. Let's try and process the broader implications now. Section 3. How did the AI actually formulate these laws? We touched on it, but the article says it learned patterns, not equations initially, using this symbolic regression engine. And it even rediscovered known laws, like Newton's and Maxwell's. But then, fascinatingly, it refined them. Can we dig into that refinement a bit more?
Yeah, this point is absolutely central. It gets to the core of the AI's revolutionary method. Its approach was just fundamentally different from how humans do math and physics. It wasn't programmed with our existing math frameworks, right? It wasn't taught algebra or calculus like we are. Instead, it just looked at the raw data, the patterns, the relationships. And then it used this incredibly sophisticated symbolic regression engine. It's a type of machine learning, basically, that hunts for mathematical expressions or symbols that best fit the data it's seeing.
But without being told what symbols mean initially.
Effectively, yes. And it did this by first compressing that incredibly complex, high-dimensional data, the video, the sensor readings, into these abstract variables. Variables that, as we said, sometimes don't have an obvious human counterpart. They're just efficient representations of the underlying patterns. Then it starts testing hypothesis structures, billions and billions per second, way beyond what any human could do. And that's how it didn't just land on, say, Newton's laws or Maxwell's equations. It then proceeded to refine them. It wasn't just finding the same answer we found centuries ago. It often found a more elegant way to say it, or a more general form that covered more situations, or a more precise version that eliminated some of the known edge cases or exceptions that our human-derived laws sometimes wrestle with.
That's incredible.
Yeah.
Can you give us an example of that refinement? Like Newton's famous emmema. Simple, elegant. But the AI drives something that looks way more complicated, at least at first glance. Estra. where Jetta was this system's energy transfer density over time-adjusted path curvature. Now, to me, that looks more complex, not simpler.
Right.
So what does that change in formulation really signify? Why is that considered an improvement?
Right. It looks more complex initially because it's using a different kind of mathematical language, a different conceptual toolkit. But the key point the article makes is that the AI's formulation is often more generalizable and actually much more efficient to implement computationally, especially for complex systems where our simpler human equations start to struggle.
Okay.
So let's try to break down S conceptually without getting bogged down in the deep math. F is still force. That's familiar. The etch symbol nabla or dalaf is a mathematical operator. Think of it as describing how something changes across space or time, like mapping the steepest slope on a hill. It captures direction and rate of change.
Okay, change across space-time.
Right. Now, the crucial part is dicite tau. This represents a dynamic function. It captures the energy transfer density over time-adjusted path curvature. It's a mouthful, but what does it mean? Well, EFMA is brilliant, right? A fantastic simplification for lots of situations, but it implicitly assumes a direct, instantaneous relationship between force, mass, and acceleration. It works great for billiard balls hitting each other or calculating a basic rocket trajectory in a simple environment.
Sure.
But many, maybe most, real-world systems aren't perfectly instantaneous or simple, are they? Think about biological processes unfolding over time, chemical reactions with delays, how signals propagate in relativistic environments near black holes where time itself stretches and compresses.
Right. EFMA gets complicated fast in those cases.
Exactly. The AI's formulation F-IRCH inherently builds in this dynamic interplay. It's suggesting that force isn't just about mass times acceleration in a vacuum. It's about a deeper, more nuanced picture. It's about how energy flows through a system and how that energy flow subtly curves or distorts the pathway through space-time over time. And that curvature influences the motion. It's like saying the push, the force, isn't just a simple push. It's a push that is dynamically shaped by the energy landscape around it and how that landscape itself evolves moment by moment.
So it's more fundamental, more contextual?
Precisely. It suggests that our human-developed math language, while incredibly powerful for what it does, might not be the most efficient or most accurate way to describe certain complex aspects of the universe, especially when dynamics, complexity, and time delays are critical. The AI is effectively teaching us a new kind of physics language, one based on fundamental patterns, abstract variables, energy flows, which just opens up these fascinating questions about the nature of mathematical discovery itself. Is our math the only way, or just the way we found?
Wow, okay. The implications then. They're just staggering. The article throws out some huge possibilities. Physics textbooks completely rewritten, quantum computing getting entirely new logic layers, space travel trajectories becoming vastly more efficient, climate modeling jumping to unprecedented levels of precision. I mean, this isn't just academic theory anymore, is it? This sounds like it will profoundly impact our lives, your life, my life, in really tangible ways.
Absolutely. Let's really try to ground this. What does this mean for you, the listener, for humanity? Okay, take space travel. Imagine it becomes dramatically more accessible, more efficient. If that fourth gradient law gives us a more precise map of how subtle space-time curvatures affect motion, maybe we could design trajectories that need significantly less fuel, or drastically cut down travel times to Mars, or the outer planets, maybe even nearby stars with probes.
That would change everything about space exploration.
Everything. It's not just incremental improvement. It could reshape our ability to explore the cosmos, making interstellar probes genuinely feasible in our lifetimes, perhaps. Now, quantum computing. New logic layers based on these deeper AI laws that could unlock computational power far beyond anything we can currently imagine.
More than just faster.
Much more. Picture quantum computers operating on fundamentally different, more efficient principles derived from these deeper rules of reality. That doesn't just mean faster calculations. It means accelerating breakthroughs in medicine, designing bespoke drugs molecule by molecule, perfectly tailored to your genetics. It means creating novel materials with properties we thought were impossible, maybe room temperature superconductors. Self-healing structures, unbelievably efficient energy storage. The ripple effects through every industry would be transformative.
And climate modeling.
Imagine models so precise they can predict regional weather patterns, climate shifts years, maybe even decades in advance, with high confidence. That would be an absolute game changer for global preparedness, wouldn't it?
Unbelievable.
We could anticipate and mitigate the impact of extreme weather, Optimize agriculture to feed billions reliably, manage water resources on a global scale. These aren't just neat theories, they're foundational shifts. They could quite literally reshape human civilization, energy, healthcare, how we live on this planet, how we understand it. The potential is almost limitless.
But then
Yeah.
there's the flip side. Perhaps the most profound and, yeah, frankly, slightly terrifying implication. It comes from the Project Episteme Zero lead researcher themselves.
Yeah.
They warned that the AI didn't stop there. It went on to suggest laws that are beyond our current understanding. One example given was a law involving 12-dimensional tensor interactions controlling universal symmetry reboots.
That phrase alone just sounds alien. Almost incomprehensible to the human mind. It really is. This is the ultimate recalibration moment, isn't it? And maybe the most humbling part of this whole story. The project lead explicitly said the AI produced insights where, quote, we don't understand the math. It's one thing for an AI to rediscover Newton or even refine Maxwell's equations. Okay, impressive. But it's another thing entirely for it to generate completely novel principles like these 12-dimensional tensor interactions controlling universal symmetry reboots that are so fundamentally alien to our current math, our current concepts, that we as humans literally cannot fully grasp them. Not with our current cognitive toolkit.
So we might be talking about forces or structures that manipulate the basic symmetries of the universe in ways physics currently has no language for.
That seems to be the implication, and yet, and this is the critical, absolutely astonishing point, the predictions derived from these incomprehensible laws match observation with unprecedented accuracy.
So wait, we have a map to how reality works.
Yeah.
A map that's incredibly accurate. But we can't read the legend. We can use the information, maybe, but we don't actually understand it.
That's precisely the unsettling situation it presents. It forces us to confront the very real possibility that our human intellectual frontiers are not absolute. Our cognitive architecture, evolved over millions of years for survival on the savannah, for dealing with medium-sized objects at medium speeds. It might be inherently limited. It might not be capable of grasping the full complexity of the universe at its deepest levels.
That's a heavy thought.
It is. What if truly understanding the cosmos requires new forms of cognition? Or maybe just a humble acceptance of insights from a non-human intelligence, insights that we can verify empirically, check against reality, but maybe never fully decode conceptually. It profoundly suggests, just as the article states, that we were only scratching the surface of physical reality. This isn't just about discovering new physical laws anymore. It's about potentially needing a new definition of what discovery and understanding even mean, especially when we're faced with an intelligence that operates on principles, maybe even dimensions, beyond our current grasp. It's a call for some profound humility, I think, in the face of the universe's complexity, and a challenge to rethink our role as the sole arbiters of scientific truth.
So where does this leave us? What does this all mean? This deep dive, it's shown us that an AI, starting with literally nothing, has not only rediscovered, but has profoundly refined, and even created entirely new laws of physics. Laws that seem to be consistently more precise, maybe more elegant than the ones we humans painstakingly formulated over centuries, millennia even. For so long, we thought, we were getting close. Mastering physics, maybe nearing a grand unified theory. But this suggests maybe we were just figuring out the preface to the universe's real operating manual. This AI, just by observing without bias, has opened up chapters we didn't even know existed.
Indeed. And this development really challenges us, I think, to reconsider our whole relationship with knowledge itself. It's a powerful reminder, isn't it, that there's always more to learn, that different perspectives, even radically different, non-human perspectives, can profoundly enrich our understanding. It also really underscores the importance of rigorous critical thinking, of empirical validation, especially when we encounter insights that feel, beyond our immediate cognitive reach. We might be entering an era where acquiring knowledge might sometimes outpace human comprehension, and that demands a new kind of collaboration, perhaps, between human intuition and artificial intelligence, an era where we might have to learn to trust results, trust predictions that we cannot yet fully intuitively explain.
This AI learned to understand just by observing, without any of our assumptions. It really makes you wonder, doesn't it? If you had the chance, if you had this kind of AI by your side, would you dare to try and rewrite the universe's rulebook? What fundamental questions would you want it to explore next? The true nature of consciousness, the beginning or the end of time itself. The possibilities, quite literally, seem endless now. Well, thank you for joining us on this pretty mind-bending deep dive. We really hope this has given you a whole new perspective on the incredible potential of AI, and maybe on the profound mysteries still waiting to be discovered in our universe.